Hey guys, I'm stopping in here during spring break to do a little math. I enjoy doing math at any time, even if it's a break. And I didn't quite get a chance to talk about something called absolute extrema during class, during our regular class, and I thought it might be helpful for you to have a video in case you want to get ahead or kind of look things over a little bit during the break. You know, a relative or local maximum or minimum is just a high point or a low point on a surface. Right? Those points, they may or not be the highest of all points or the lowest of all points. They might be relatively the highest or lowest point. I could be standing on the top of a mountain, and at least locally I'm at the highest point. But there might be other mountains in the distance that are taller. When we talk about absolute maximums and absolute minimums, we are looking for the single highest point on the surface, the highest of all of the highest points. Okay? Now, one of the things about absolute maximums and minimums is that we have to have a domain in place. I want to find the highest point where? The absolute highest point where? If I say California, that would be the top of Mount Whitney here in California. But if I say where's the highest point in the world, the absolute maximum on that domain would be Mount Everest. Okay, so the absolute maximum and minimum values, they depend on, this depends on the domain given. They always have to give you the domain. Okay, so you're going to be seeing problems where they actually give you the domain. And you're only looking for the highest and lowest points in the domain. Just within that domain, just within California, the absolute maximum would be Mount Whitney. Okay? So it depends on the domain. If I change my domain, my absolute maximum and minimum might change. Okay? So that's one thing to keep in mind. Let's actually write down the definition here of an absolute extrema. Okay? So an absolute maximum, so this is different than a relative maximum. An absolute maximum of f, that's my function of x and y, on a domain, let me call my domain capital D for a minute, okay, is a point AB in that domain D. It's a point in that domain D with f of xy less than or equal to f of AB for all xy in D. Okay? So not just f of AB is not just greater than or equal to f of xy near the point AB, but throughout the whole domain D, we're looking at the highest point. Okay? And then, of course, similarly for absolute minimum. Okay? Now, one of the theorems about this is that as long as your domain is closed, all right, if D is a closed region, that means it includes its boundary. The edge of the region is included in it, right? Then in that case, then F must have an absolute maximum and an absolute minimum. It has to exist. These things have to exist. Let me just remind you, back in first semester calculus, if I take a function like this, right? Let's say my interval is from A to B here. If that's a closed interval, and I'm including the boundary, which is the endpoints of the interval, then I'm going to have to have an absolute maximum. There it is. That's the highest point of the function on this domain. I also have to have an absolute minimum. That's this point right here on this domain. So the thing is that if you exclude the boundary, if you exclude the boundary here, then you're not allowed to use this point anymore. I take it out, and now you see there is no highest point of the function on that open interval, because I'm not including the edge of the domain here, right? When you're looking for your absolute maximums and minimums, you're going to look for places that are flat, like this point right here. This is a critical point, right? There's another one right here. It's flat right there. It's another critical point, C1 and C2, in the interior of the domain. But if you include the boundary, right? If I fill in the boundary, then those boundary points, even though the function is not flat at the edge of the domain, those boundary points are still in the running as candidates for the absolute extremums. And here you see that this actually is an absolute extremum. Okay? So if even more obvious example would be just a straight line like this, right? If I include a closed interval, right, then that function is never flat. There are no local extrema. There are no critical points. The derivative is never 0. But at the edge of the domain, I have included the edge of that domain, and that's where I'm getting my absolute minimum and absolute maximum value on that closed interval. So it's possible, though, if I don't include the boundary, if I don't include the edge of the domain, it's possible this function right here has no absolute maximum or minimum at all. There is no highest or lowest point on that open line segment, okay? Because I'm not allowed to go all the way to where the open circle is, and there is no biggest point that's right next to that open circle, right? I can get as close to that open circle as I want without actually touching it, okay? So in order to guarantee an absolute maximum or minimum, I have to have a closed interval in this case, or in the Math 251 version of this, I have to have a closed region. The boundary of the region has to be included. So now let me explain to you what you really want to know, which is how do you find these absolute extrema? What is the procedure? So to find absolute extrema, we have a nice process here. Okay? The first process is find critical points within D. Find the critical points that are within the domain. Now, if you find critical points that are outside of the domain, then you throw those away. Those are not going to be considered if they don't occur within the domain. Remember, the domain will be given. They have to give you this domain D. They're going to tell you what it is. If you find critical points that are not in that domain, well, those critical points can be ignored, basically. Okay? The second thing you have to do is find the extreme values on the boundary of D. Now, guys, if D was not a closed domain, you wouldn't have a boundary. The boundary would not be included, and there would be nothing to do in step 2. Okay? So most of the time you're going to have a boundary, you're going to have a closed region. Okay? Because it could happen that you could get shut out here. Maybe there are no critical points, and if you have no boundary, then you're not going to get any points here out of these first 2 steps. The third thing that you do once you have all of these points that you've come up with in steps 1 and 2 is you compare all candidates coming from 1 and 2. So all of the candidates that you found, you just take all of those and compare them, and you take the largest and smallest values. Okay? You're going to take the largest and smallest values. That's going to be the answer. Okay? Let me do one example of this for you, and then I'll let you work on it, and we'll talk about it after the break. Okay? I'm going to do one example. just to kind of show you this three-step process. It's a nice three-step process. So here's an example of finding the absolute extrema of a function. Let f of x and y be equal to 1 plus xy minus x minus y. Let's take this function right here. I'm going to tell you what d is as well. So let d be bounded by the parabola y equals x squared and the line y equals 4. Okay. So it helps to draw a picture of your domain. I think that's a good thing to do. The parabola y equals x squared is, of course, right here. And the line y equals 4 is like this. So you see that it makes this domain D right here. This is going to be my region. It's a closed, bounded region in the xy plane. All right? The points where the parabola crosses the line, you can figure this out pretty easily, is negative 2, 4, and 2, 4. All right? So there is my domain. So let's go through our process here. The first thing I need to do is find all of the critical points that are in the domain. Okay, well, we know how to find the critical points. We take the partial derivatives of the function and we set them equal to 0. So with respect to x, I'm going to get y minus 1. And when I differentiate with respect to y, I'm going to get x minus 1. When you set those equal to 0, you very quickly get just one critical point, which is the point 1, 1. X equals 1, y equals 1. X equals 1 and y equals 1, just make one point out of that. Now that point is actually right here on the domain D. It's right on the edge of that domain. Okay? So we have this point 1, 1 that's on the edge of the domain right there. Okay. There's no need to test this one right now using the second derivative test. We don't need to classify this point. Remember, all we're going to do when we're finding the absolute extrema is make a list of candidates. So this is one candidate that we have, but we're not done yet. We're going to look at step 2 before we finalize our list. But we're going to just take all of these candidates and make a list of them, and then we'll take the largest and smallest values that we find. We don't have to actually classify these critical points like we did earlier with the D test. I'm not going to do that. I'm just going to make a list of these points. Okay? It's because at the end of the day, we're going to be taking all of these candidates and we're going to find the largest and smallest values anyway. That's what step 3 is all about. So we don't need to stop right now and do any more calculations. Let's look at the boundary of the domain. So step 2. So this was step 1. Step 2, the boundary is made up of 2 parts, right? There are 2 parts to this boundary. The first part is the line y equals 4. That's the part up here on the top, okay? So what I'm going to do is I'm going to literally plug 4. I'm going to take my function f of x and y, and I'm just going to put 4 in for y everywhere that I see it. So I'm going to get 1 plus 4x minus x minus 4. In other words, 3x minus 3. It's now a function of only x, right? Because I've substituted a specific number for y. If I take the derivative of that, I get 3, which is never 0. In other words, this function, if I look at my function as I'm on this line segment, right, there is no place where that function is flat. This is just a regular derivative because there's only one variable here, x. I've gotten rid of the y variable because I'm only focusing my attention on the line where y equals 4. So I only have variation with x, but the derivative of that function of x is never 0. So you're not going to get any critical numbers out of that. However, you do have, just like I showed you before, if this is a function of x, you do have the boundary between -2 and 2. If I just think of it as a function of x only, it's a function from -2 to 2, and I do need to look at the endpoints of that domain. So I have to look at the endpoints and throw those into my list. So in other words, -2, right? So -2, of course, the corresponding point is 4, and For positive 2, the corresponding point is 4. These are the y values in the second slot. And in the top part of this domain, y is equal to 4. It's just a constant value of 4. So look at my list of candidates. I've got this one right here. And now I've got these two. The edges of this parabola, basically. Finally, I have one more part to my domain. I need just a little more room. Let me see if I can squeeze it up here. Part 2, which is the parabola itself, y equals x squared. If I put that into the function, if I put y equals x squared into the original function here, right, I'm going to get 1 plus x cubed minus x squared. And that I can, once again, differentiate. I'm looking for critical numbers, and I'm going to set this equal to 0 again. If you solve that parabola, you're going to get, it actually factors, 3x plus 1 times x minus 1. So you get x equals 1, or x equals negative 1/3. Of course, when x is equal to 1, now you're going to use this equation to figure out what y is, because you're talking about points that are on that curve. Well, y is equal to 1. And negative 1/3, when you square that, y is equal to 1/9. So what points do I get here? Well, again, I get the point 1, 1. We already had that. We're getting it again as a candidate. And then we're also getting the point negative 1/3, comma, 1/9. All right? So what is my full list of candidates here? Well, my full list of candidates turns out to be, I have 1, 1, I have negative 2, 4, I have 2, 4, and I have negative 1/3 and 1/9, right? So that last point is negative 1/3, 1/9 is right about there. So these 4 points that I have highlighted on this domain D, they're all on the boundary, as it turns out. It just happens to be that way. It won't always be that way. But in this case, there are no candidates, there are no critical points inside of D. Okay? If D was not a closed region, if it was not including the boundary, I would lose all 4 of those points. And I would suddenly have no critical points at all. I would have no maximums or minimums necessarily to find. But in this case, I do have these candidates. I'm going to plug each of them into the function, the original function. I go back to the original function now, and I plug those points into the formula. If I plug in 1, 1, I'm going to get 0. If I plug in negative 2, 4 for x and y into this function, I'm going to get negative 9. So I'm just telling you the values here to save some time. 3, and then this one is 28 over 27. And guys, you see right away, negative 9, that's your smallest number. This is your absolute minimum value. It's the smallest of the 4 numbers that you came up with. Your absolute maximum value is the biggest of the 4 numbers that you came up with, and that is 3. So that's step 3. Compare all of the candidates that you obtained through this process. We came up with 4 candidates, right? So you take all 4 of those candidates and you keep the biggest number and smallest number, and that tells you the absolute minimum value and the absolute maximum value. All right, I hope that this was helpful. I've got about 2 or 3 homework problems for you to practice this method with. The nice thing is you never have to use the D test. You just simply find the candidates that might be maximums, might be minimums, and then you just plug them all in. So there's no D test here. You're just taking the critical numbers, that's what we did in the critical points from step 1, together with the points on the boundary that are critical points of the boundary. And you just throw them all into a pile, and then just test those points that are in that pile, and that's how you get the maximums and minimums. These are the absolute maximums and minimums. Okay, thanks a lot. I hope that made some sense, and we'll talk about it again soon. Thank you.